Hello and welcome to 32nd lecture in the 19th chapter. We are at present doing kind of wrap up the entire chapter, and in this lecture we want to discuss about how to choose the correct hypothesis test, because we have seen one sample t test, two sample t test, paired sample t test, then z test, then chi-square test, ANOVA, maybe one another was also there. But the point is which test to use in which circumstances. Then as such we did detailed discussion, and I took care that each lecture takes only one test, and it was around 35 to 40 minutes minimum discussion on each test. But still, this is a nice little summary of a guideline what test is more applicable in which kind of data. First, let us see on which factor the selection of test depends. Then, selection of appropriate statistical test depends upon 1. Type of data, 2. Number of groups, 3. Distribution of data, 4. The sample size which is available to you, and 5th, the type of comparison that you want to do. So let us take each. Type of data. If the data is continuous, for example height, income, temperature, then the test like correlation test, Pearson correlation, they will give better insight. But if the data is categorical, for example gender, yes, no responses, etc., then chi-square test would give better insight. Number of groups. If there is a single group only, but you want to study the effect after your intervention and before your intervention. For example, one group of employees you have selected, and you measured their productivity before making them undergo a training program, and you measured their productivity after making them undergo one training program, and it was found that, or rather you are assigned a task that from these two situations of same sample, you decide if the training program is effective or not in enhancing the productivity. So same group is there, one group before and after training, so one sample t test. But if two groups are taken, then for example same training program example, but you divide your employee into two parts. Say 50 employees undergo the training program and 50 employees do not undergo the training program. All have the same productivity rank assigned by the HR department before you do your experiment. So that means in all other ways there are both are independent samples, and now you study them. So at that time two sample or paired sample t test, that is more appropriate. Then if there are 3 or more groups, then we know that this t test etc. are only for 2 groups. But if there are 3 or more groups, then you will use ANOVA. Now distribution of data is equally important. If the data is normally distributed, because that is the basic assumption for using central limit theorem, then in that case our routine hypothesis testing methods are applicable, and you can check if data is normally distributed or not with histogram and KDE plot with that, QQ plot, quantile plot, or test like Shapiro-Wilk test. Now this word is coming for the first time, but whenever we will move further in the other chapters, you will see that sometimes we would like to conduct this test to decide if the data is indeed normally distributed or not. Okay. So if data is normally distributed, then the test whose assumption is normal distribution, for example Z test, is the most easiest and the convenient test. But if the data is not normally distributed, then in that case you will have to use non-parametric tests. Okay. Sample size. Again, sample size is an important assumption in central limit theorem, that each sample must have 30 or more members or data points. Now, if 30 or more data points are there, large sample is there, and normality assumption is also obeyed, so central limit theorem will be obeyed. Then use, for example, Z test. But sometimes the sample is very less, small in size. Maybe only 10 observations are there. So at that time you will use t test or other non-parametric tests. Okay. Then type of comparison. So mean, proportion, or association, what you are comparing. And this is a nice little table. In first column, scenario is given. In second column, the type of test which you will use in that scenario is given. And in third column, and a practical example is also given. So for example, if you are asked to compare sample mean to a population mean, for example, monthly sales are 5,000 across all the branches of your large retail chain, which has 5,000 or maybe 10,000 stores across our entire country. Now, obviously, you are not going to do your experiment in all 10,000 stores. You will select maybe some 60 stores or 80 stores as a sample, and decide if monthly sales is $5,000 or not. Now, if that assumption is correct, alternative hypothesis or say null hypothesis is that monthly sales is $5,000 and that is correct, then in that case you will say that the question which arises is that was just for a sample of 80 stores, but will it be applicable to 10,000 stores? That is, will it be applicable to entire population? Or in other words, this is the mean monthly sale for 80 stores, but is the sample mean same as the population mean for the 10,000 stores all over country? So for that kind of case, you will use one sample t-test. Now, sometimes you need to compare two independent group means. Okay. For example, testing if male and female employees have the same average salary. So in your organization, you will take a sample of all females and another sample of all males, find their mean and compare them. Null hypothesis is that both have same mean salary, and alternative hypothesis is that both do not have same mean salary. Now here you are comparing two totally independent samples, so use two sample t-test. Compare two related group means. So that is, there is only one sample, but you want to study the effect before making your intervention and after making your intervention. I already gave one example that you have a sample of employees, so you measure their productivity before a training program and after a training program and decide if the training program is effective in improving the productivity. This is one another example that you have one sample of patients, you measure their average blood pressure, okay, and all are patients of hypertension, that is high BP. So you measure their average blood pressure before giving them some medication and also measure after giving the medication and check if the medication is effective in dropping the blood pressure or lowering the blood pressure. So sample is same, but you want to study the effect before intervention and after intervention. So at that time, paired t-test. Compare three or more group means. There you can use ANOVA. For example, you are going to employ three different possible marketing strategies, and you want to choose which out of the three is the best marketing strategy so that you can use the best possible. So you make three different samples of your customers and subject them to each marketing strategy. So here there are independent samples and the number of strategies are more than two, three, or it may be five different marketing strategies. But in short, more than two different interventions you are doing, one on each sample. Then you measure the monthly sales or average sales for each group, find the mean value and decide which mean is the highest. Suppose the mean for the marketing strategy number 2 is the highest average sales. So in that case, you will say that the marketing strategy 2 is the most effective. So you will discard marketing strategy 1 and marketing strategy 3 and you will use only the marketing strategy 2 for entire population. Then if you want to test association between categorical variables, as soon as categorical comes, chi-square test is clear. Okay. For example, if product preference depends upon gender or not, or if product preference depends upon age group. We took the example of that shaving cream and three different age groups, but in that case we found that age has nothing to do with the liking or disliking of the product, right? Then test correlation between two variables. Now correlation is always tested for continuous variable. So use either Pearson correlation test or another is Spearman correlation test. Okay. For example, if you are asked to test this particular thing, that are the number of hours studied and the exam score correlated. So is it like that more hours means more exam score and less hours study means less exam score? Okay. So in that kind, Pearson or Spearman correlation test is more applicable. I told you its limitation also that it measures only linear correlation. So for non-linear correlation, you can use Chatterjee correlation test or other correlation test. Now, this is also same thing given in a particular table. This is same thing, but given in a kind of that decision tree. That suppose this is how your thought process should go. That I am asked to conduct a hypothesis test. So first, what kind of test it is? Is it relationship between variables or is it comparison between means? Okay. Suppose it is relation between variables, then what kind of variables are there? One, are both variables normal or they are interval types and ratio types? Okay. If all variables are normal, then use chi-square test. But if all variables are interval and ratio types, then use correlation test, because interval or ratio can be defined only for numbers. That is clear because you can't say what is the ratio of male to female. That means ratio of number of males to number of females, that is a different thing. But what is the ratio of male to female, two categories? Or what is the ratio of manager to officer to clerk. Now that kind of words are meaningless. For categorical variables, they are meaningless. So that is why ratio or interval are meaningful only for numeric variables. So you will do correlation analysis. Okay. Now suppose here this was the path which you will take if you are asked to find relationship between the two variables. But suppose you are asked compare the means. Then what you are comparing? Are you comparing sample mean to the population mean, or are you comparing one sample mean to another sample mean? Okay, you are comparing sample mean to population mean. Then do you know samples? Population standard deviation. Here something is missing. That is, do you know population standard deviation? Okay, if yes, then you can use Z test. But if you don't know, no, then you can use one sample t test. Okay. Similarly, suppose instead of comparing sample mean to population mean, you are comparing the means of two different samples. Then are the samples independent? Yes or no? If yes, independent, then use independent sample t test. If not, that means they are paired samples. Then you use paired sample t test. Okay. So this is how one can decide which test to conduct. So these two tables are very important because, and this table and this diagram, they are very important because you may know everything about each type of test, provided someone tells you that perform this test. But in field work, no one is going to tell you. You have to decide the business situation, study the business situation, and you have to decide out of given possible tests, out of available possible tests, which test to use. Okay. Then this is also important. Common pitfalls and best practices in hypothesis testing. There are certain common pitfalls. This is one. This is second, third, fourth, fifth, and sixth. So we will do it. Particularly the first one is very important. Misrepresenting the p-value. Now, suppose you have one this kind of null hypothesis that the given drug, a new drug is introduced, a new medicine for say blood pressure or some other health condition. Then as a drug approval authority, you are supposed to test it whether the drug is actually effective or not effective. Okay, for which we have done the discussion earlier also, that you will decide this by making two samples. Suppose it is a drug for hypertension, then you will make two samples of hypertension patients, high blood pressure patients, right? One sample will have this new drug which is to be introduced given to it, and second sample will be given placebo. And null hypothesis will say that the drug has no effect, or in other words, the first sample which takes the drug and the second sample which takes the placebo both have equal effect on the hypertension. That means there is no effect due to the drug. Okay. Alternative hypothesis says that no, the sample which takes the medication, its blood pressure decreases significantly compared to the sample which does not take the medication, or that means the sample which takes the placebo. So that means the drug does have an effect. That is alternative hypothesis. Now suppose you decided that 95% confidence interval is sufficient. Now in that case, you got a p-value 0.04. Now how to interpret this p-value? There many people do not stick to the scientific and strictly strictly statistical terminology. So we say that if p is less than alpha, now here my alpha is 0.05 and this is 0.04, right? So if p is less than alpha, then null hypothesis is rejected. But that does not say that means alternative hypothesis is accepted. No. Entire interpretation of p is always in terms of null hypothesis only, because p is the probability that your response falls within the distribution under null hypothesis, right? So if p comes out to be 0.09 greater than alpha, then you will say that null hypothesis is accepted or valid. But if p comes out to be less than alpha, then you will not use word that alternative hypothesis is accepted. No, you will just say that null hypothesis is not valid. So that means that the drug has no effect. That much we can say with this statistical test. But it does not give the guarantee that the alternative hypothesis is correct, or that means that drug does not have effect. That much is okay. But is it a guarantee that means that drug will help to lower the blood pressure? Then there is no such guarantee. So you should always speak null hypothesis is valid, or if alternative hypothesis is correct, then you don't speak alternative hypothesis is correct. You just say that we fail to reject null hypothesis. For example, if p value comes out to be 0.09, so p is greater than alpha, alpha is 0.05. So you will not say that we accept alternative hypothesis or we accept null hypothesis, you will just use that kind of word. We fail to reject null hypothesis. So the word accept this hypothesis or accept that hypothesis, that are not there. Either null hypothesis is rejected or we fail to reject null hypothesis. If our p is less than alpha, null hypothesis is rejected. If p is greater than alpha, we fail to reject null hypothesis. That's all. That is the classic and the uh, what you call scientific statistical method way of describing things. It is a different thing that sometimes even I use sometimes that kind of word, that null hypothesis is not valid, so we accept alternative hypothesis. But in strict terms, null hypothesis is not valid. That does not give any guarantee that alternative is valid. Okay, that just says that we fail to reject null hypothesis or we succeed to reject null hypothesis. That's all. If p less than alpha, then we will say that yes, we can reject null hypothesis. If p is greater than alpha, then we will say that we fail to reject null hypothesis. So please remember that. Say p value below the significance level does not prove the alternative hypothesis. So if p is less than alpha, it does not give a proof that alternative hypothesis is accepted or correct. It simply suggests that there is an evidence against null hypothesis. So it will say that we are successful in rejecting null hypothesis. Similarly, a p value greater than alpha does not prove null hypothesis is correct. It just suggests that there is insufficient evidence to reject null hypothesis. So that is why that term, we fail to reject null hypothesis. So if you get, for example, that new hypertension drug example, and you got p is equal to 0.04, then it does not mean that there is a 4% probability that the drug has no effect. P value does not measure the probability of H0 or HA being true. It only evaluates the compatibility of observed data with the null hypothesis. It is the probability that the observed data, that is observed outcome, false according to the data distribution which is described by null hypothesis. It is compatible. That's all. Okay. It does not guarantee that drug works. So p value less than 0.05, that means you rejected the null hypothesis. That is fine, but that does not give the guarantee that the drug will have effect. Of course, it says that we can tentatively accept alternative hypothesis. But as I said, there is nothing like tentatively accept in strict terminology. Strict terminology, you can say that yes, we succeed to reject null hypothesis. But that's all you can say. So we succeed to reject null hypothesis means that this sentence seems to be wrong. Drug has no effect. But that tentatively says that drug works. Okay. However, that is not absolute proof, and some further studies or replications are necessary. That is why it is so difficult to get approval for the new drug from FDA, Food and Drug, that is the approval authority, US FDA or Indian Drug Approving Authority, because they will most of the time not accept just one or two experimental or a small sample experiment. They will tell that, okay, your one test has given this kind of result and drug seems to have effect. Fine, now do it by other test, do it in other sample. For example, one way of doing the test is, as I said, expose some patients to the drug and expose some patients to the placebo. Similarly, other way of doing the experiment would be measure the blood pressure before giving the drug and measure the blood pressure after giving the blood. So that is different way of taking. Then take a different sample from different patients who have different genetic constitution, and then you can, if your drug passes through multiple such tests, then only it is accepted. So that is one thing. Okay. So a low p value like 0.04 just increases the confidence. It says tentatively your drug is working. It increases the confidence that the drug might have effect, but it is not definitive. It is just one piece of evidence in the larger puzzle. Okay. And therefore, all practical decisions like approving a new drug should consider many other things. What is the size of effect? Sometimes it is possible that p value comes out to be less than 0.05, but in all these patients, the blood pressure did reduce, but maybe it reduced by 2 millimeter of Hg. So is it that large enough effect? So how large effect? What is the confidence interval used? So is it justifiable to use 95% confidence interval for sensitive things like healthcare? So maybe the approval authority tells you that no, do the experiment with 99% confidence interval. Okay, external validation. So that is what is called that peer comparison. Whenever a new research is done, like presenting a new drug, etc., then peer validation is also important, in which same experiment is then done by other statisticians or other pharmaceutical companies and all, and they also, if they validate, then that gives another piece of evidence. So all these pieces of evidence meet. Okay, so that is the first important and the most important pitfall in hypothesis testing. Please remember that p less than alpha does not mean alternative hypothesis is correct. It just means that we can reject the null hypothesis, and these two terminologies are totally different. We reject this, nowhere says that we accept this. Okay, Then second pitfall is neglecting the assumptions. For example, if your test assumes normality or equal variance or independent samples, but you conduct the test without checking your data for normality, or your data did not obey normality and still you carried on with your test. Equal variance was also not found, but you carried on with your test. While taking samples, you were not careful and therefore samples were not independent. So in that case, even though you conduct the test perfectly, you have violated the basic assumptions. So incorrect conclusions will come. For example, t-test on highly skewed data without checking normality can produce misleading results, right? Now, another also I said that Cauchy distribution. If your data has Cauchy distribution, now the problem with Cauchy distribution is that it has infinite means and infinite variance. So that assumption that finite variance is not obeyed, right? So in that case, central limit theorem itself is not applicable. So entire hypothesis testing will collapse. You have to go for non-parametric test. So this is one example that a study compares pre and post intervention weights using paired t-test, but ignores that right from the beginning, the weight data was skewed. So even before your intervention, whatever sample you selected, that was highly skewed data. So what is the best practice? That you do your pre and post intervention weight using a paired t-test, right? Sorry, what is the best practice? Use a non-parametric alternative. For example, don't use paired t-test, but use this Wilcoxon signed rank test if normality is violated. So it is not that normality is not obeyed, then everything is lost. But then you will have to use some advanced test. This is that kind of test. Okay. Overemphasis on statistical significance. Okay. Sometimes what happens is statistical significance occurs. That means your p-value is less than alpha. So you say that yes, there is statistically significant evidence that new marketing strategy will improve the sales. Okay. But it may not be practical. It may not make sense from business point of view. For example, you get statistically significant increase that sales will increase by $1 per month by new marketing campaign. But if the cost of that marketing campaign would itself be $30 per month per user, and as a result the sale increase is $1 per month per user, then is it justified? Though statistically it is perfect, correct? Statistically significant. Yes, marketing campaign affects the sales, but you have to think from business point of view also, right? So then you can say that the magnitude of the effect also you have to think, and the amount which you are going to spend on your intervention, that also you have to decide, right? Then there is something called p-hacking. Now many times people start with the wrong approach. They already decide that I want to get this conclusion from my statistical test, and they go on trying different combinations of features, or different way they go on manipulating data. Sometimes they will normalize it, or sometimes they will do min max scaling, sometimes they will do outlier removal, even though the domain was such, like say credit card fraud detection, where outlier removal was not to be done, but still they do everything and somehow bring the p-value according to what they had decided. So they had decided that I want that null hypothesis should be invalid, that they bring the p-value less than alpha. Or if they have decided that null hypothesis is valid, then in that case they will bring the p-value greater than alpha, and until and unless they don't get the desired p-value, they will go on manipulating the data. Okay, that is called p-hacking. For example, testing various subsets of data until finding a p-value below 0.05 without adjusting for multiple comparisons. You take first subset and second subset and third subset, then are you taking enough care that each subset is independent, and are you using your statistical tests with proper adjustment for multiple comparisons and all that? Then this is called p-hacking, that somehow you hack your way through the desired outcome. Okay, so that is not at all to be done, right? So a data scientist analyzes 20 features to find any significant correlation with the target variable. So that means he says that let me study 20 features, and if any of them somehow gets a significant correlation with the target variable, then I will go with that feature. And for that, he goes on comparing that 20 feature, maybe before normalization, after normalization, and multiple comparison, right? And by chance, he finds out that one feature has p less than 0.05. 19 features are not having, but one feature has p value less than 0.05. But it is possible that this occurred just by chance due to multiple comparisons. So you have to take care that your result is not just by random chance. So some corrections are done for multiple. Here this word is written, adjusting for multiple comparisons. So for multiple comparisons, you have to apply some corrections. For example, here there is one such correction which is very popular, that is called Bohm-Ferroni correction. Or you can split the data into training and test set so that you can reduce the bias, right? So this is one thing where one has to take care. P-hacking is strict no-no, and you should not do it, because that is kind of fooling yourself. There is one saying in data science that if you torture the data sufficiently, then it will confess to anything. So you should not do that. Okay. Ignoring effect size. Sometimes it happens that small p-value, right, you got that there is a significant effect, but effect size is also not important parameter. So we also earlier also did that, that if you spend $30 per user for marketing campaign, and if you get $1 increase sale per user, then that is okay. Statistically, you have proved that by spending money on marketing, your revenue increased, but the magnitude of effect is negligible. So you can use this type of test like Cohen's DD, R squared, etc. So that effect size also is taken consider, and you are giving your results in proper context. So a new teaching method may show statistical significance in improving test score, but average improvement could be just 0.2%. So will you subject all the thousands of teachers all over your country to the new teaching method, or force them to employ new teaching method because you found an evidence that average improvement of 0.2% is seen? It is possible that that average improvement is just by random chance. Okay, so the whole effect magnitude of effect is very small, effect size is very small, so it is not worth going for a costly teachers training program, right? A retailer test that if new layout increases the sales and find the p-value 0.03, so that means null hypothesis is that I change the entire furniture in my showroom and my sales increase does not change. That is null hypothesis. An alternative hypothesis says that by changing the layout and the appearance of my retail showroom, the sales does change. Okay, now assume that you are a big chain retailers like Zudio or something, which is a brand of Tata's. So there you have to change the layout in maybe 800 stores all over country, and you can understand the budget. That is, you have to change the furniture, change the layout, put new glasses, and the old things will be perhaps thrown away, and so on. A costly endeavor. But if it increases the sale by, that is what your statistical evidence also you got, that p is less than, then the question is that would you blindly go for changing a layout? No, you will ask for the magnitude, what is the size of effect, because if you find that the sale increase is only 0.5%, then you will not go for it. So a good practice is that you don't not only report, when you create the report of hypothesis test, not only report the conclusion, but also report the size of the effect, so that proper business decision can be taken. One more last pitfall is inadequate sample size, because we know that greater than 30 is the minimal requirement for central limit theorem to be obeyed, and if central limit theorem itself is not obeyed, then many more things will be non-applicable. But if you have a small sample size, then it may lead to type 2 errors, that is failing to detect a true effect. Okay, so then conversely, a very large sample size might take some trivial effects as statistically significant. Trivial effects like which are noise, which are there by just random chance, they will also look statistically significant if you take a sample of 1 lakh data points. Because the sample should be greater than 30, then why you will take so many data points? You will take maybe 100, 200, up to that is fine, right? For example, detecting 0.01% increase in the take-through rate with a sample of 1 million users. Now that is because you have perhaps picked up some noise, some random chance, and therefore this increase was recorded. So this sample is itself wrong. A startup test user satisfaction after a feature launch using sample of 10 users. Now this time sample was very large, but here now with this startup, the sample is of only 10 users. So that means the sample is very small. So it violates the central limit theorem. So whatever results it gives, they are irrelevant, and that means that the test will become inconclusive. So there is another kind of analysis which is called power analysis. That power analysis can help you with what is the minimum sample size required for the given data and given domain and given test case. So that greater than 30, that is just a generalized way, but thereafter you can, for a particular specific business case, you can get greater than 30 means how much? Say 100, 150, 90, that you can get exact number that this much sample is optimal sample by using power analysis. So these are some common pitfalls and how to avoid those pitfalls and what are the best practices. Now here our hypothesis testing, everything is over, but the heart of hypothesis testing lies in central limit theorem. We know that if central limit theorem is not obeyed, then hypothesis testing would not be able, will not work, because that whole thing that you are measuring mean for a sample and you are translating that under certain assumptions, the sample mean and the population mean, they are very close to each other within a certain confidence level, right? But that question is that without central limit theorem, hypothesis testing cannot be done. So here we will take some more examples of central limit theorem. these are those examples in which no ready-made test is there. So that is why you will see that here we will not be importing any test. We are not importing any test. So you have to design your custom test, you can say, a kind of custom test, and decide if the problem is solved or not. Here also you can see you are not importing any test. Of course, norm you are importing, so maybe the Z score you are finding, yeah, Z score here you are finding, right? Okay, fine. Then here also norm you are finding, so Z score you are finding, okay. But these are those kind of cases where you have to go by definition, because you know that there is no import Z test in from the scipy.stats library. Okay, so we will take these three examples in next lecture, which will become our last lecture, and there the chapter will become officially over. Here exercise questions start, but chapter will be over here. So it will be a small lecture, that is fine. So we'll see in the next lecture. Thank you.